All right. So today we're doing aspirin synthesis. And I know this is really strange, but just bear with me. And today is September 6th. All right. And if you if you watch the video that I sent out, then you've already seen the mechanism. And I'm not sure. Well, let me take that back. You haven't seen any mechanisms up to this point if you're taking part one. I know there are a couple of people in here that are in part two, but taking part one lab. But you haven't seen the arrow pushing and all of that stuff. So I'm actually gonna kind of give a little crash course on that before we do the walkthrough. All right, so you have salicylic acid. Right, and I'm reacting this with acetic anhydride, which is this compound here. Right, and the goal of the reaction, I'm gonna write it this way. I'm gonna treat this with sulfuric acid. The goal of the reaction is to actually take this alcohol functional group right here and do what we call acylate it. So the overall reaction is an acylation of that alcohol group. Right, so let me draw the products. So this is one of my products. This is the actual aspirin itself. And when you think about aspirin, everybody here has taken aspirin at some point, unless you're allergic to it. But Felix Hoffman, who was the he wasn't the inventor of salicylic acid, but he discovered that acylating salicylic acid, it lessened the side effects of taking aspirin, one of which is damage and irritation to the esophagus, right? And so this is one of this is the main product. This is aspirin, or acetyl. Right, the acetyl part is this piece right here, salicylic acid. All right, so it's that, and then what's left over from acetic anhydride is acetic acid. Right, so a quick and dirty way to think about this is you're actually taking this group right here, and you're using that group to acylate that alcohol, right? And that's how you get the acetylsalicylic acid. And then the other part of this anhydride, which is here, that's where your acetic acid comes from. So anytime you make aspirin, it is a the type of reaction it is, it's an addition followed by an elimination. So I'm gonna show you that part. Even though we haven't discussed arrows yet in class, we will, and there's no time like the present. So in the mechanism, what a mechanism is in organic chemistry, it is a depiction of the steps of a reaction, right? It tells you how you get from reactants to products. So steps in a reaction, and I'm going to abbreviate reaction. Anytime you see that RXN, that's just a shorthand for reaction. So we get from reactants to products. right? Every chemical reaction is the same. You start with a set of reactants, and then you convert those reactants into product using some type of transformation, right? So in this case, let's walk through it. So we have salicylic acid, which is here. I'm gonna put the lone pairs in so you can see how this works. And then you have acetic anhydride, which is here. So what we have talked about up to this point is bonds, right? The types of bonds. And I think we left off Friday before the break talking about polar covalent bonds. So this reaction takes place here at this carbonyl and here at this alcohol. That's another, we're going to start functional groups next week, but again, this is another another place where we can introduce some useful information. So this is an alcohol, right? And this over here is a carbonyl. It's a generic name. The specific name is anhydride. Right, this is the structure of an anhydride right here. Right, the groups out here can vary, but that central part is really important where you have a two carbonyls connected by an oxygen. That's the central structure of an anhydride. Right, so the alcohol and anhydride react together, and this is an example of what we call an addition reaction. Can somebody tell me with the carbonyl, what is that double bond composed of? Anybody?
A pi and a sigma bond.
A pi bond and a sigma bond. And so anytime you do an addition reaction, this only occurs on pi bonds or compounds with pi bonds. Let me rephrase that. Right, there are four types of reactions. You have addition, substitution, elimination, and rearrangement. So this reaction falls under the classification of an addition reaction, right? So what you're gonna, in an addition reaction, you add, and I'm gonna explain all the terminology too. Add what we call a nucleophile to a pi system. And that pi system is what we call an electrophile. Right? So all of these types of reactions that are polar like this are going to be between a nucleophile and an electrophile. So the nucleophile in this case is going to be the alcohol. Right? This is a lover of nuclei. That's what nucleophile, the phile is from the Greek word philos, one of the words for love. So a nucleophile is a lover of nuclei, right? And every nucleus of every atom has a positive charge. Right? Because in the nucleus, that's where your protons are. Right? So the nucleophile is a lover of nuclei, and then the electrophile, which in this case is here. What do you think that is? Just by intuition.
Lover of electrons?
A lover of electrons. Very good. Excellent. It's a lover of electrons. right? So that's what we're doing here. We got a nucleophile, we got an electrophile, we're going to put them together, and then magic happens, right? And so the way to illustrate a mechanism in organic chemistry is to use what we call double-headed arrows, right? And we use curved arrows, right? So if I want to show the nucleophile interacting with the electrophile, right? And this is, again, I think I said this on Friday in class, this is polarized towards oxygen because it's a polar covalent bond. Oxygen is partially negative, this carbon is partially positive. So anytime a nucleophile attacks an electrophile, it's going to attack at the site that's most positive or most partially positive, right? So the way I'm going to show this is I'm just, and you don't panic if this is not clear, because we're going to have a whole section on this during lecture. But I want to show this here. So I'm going to draw an arrow from the electrons on oxygen attacking that carbonyl. If I leave that how it is, what would be the problem with this carbon right here? Anybody? How many bonds can that carbon make?
4.
4. If I don't change anything, and the arrow is indicative of me making a bond between oxygen and that carbon, how many bonds would that carbon have if I don't change anything? Because it already had. Speak up again. Say that again. Sorry.
It'd be 5.
It'll be 5. So when I attack this pi system, right, I need to break a bond. So the pi bond is the easiest one to break. So I'm going to take that pi bond. It doesn't matter which side you use, but I always pick the outside bond. I'm going to give those electrons to oxygen. All right, so that's the first step in the mechanism. That's the first thing that happens. Oxygen attacks the pi bond. I'm not showing the acid catalysis. I showed that in the video, but I'm just going through the nuts and bolts real quick before we get started. So oxygen is going to attack the carbonyl, and then you're going to end up with the intermediate that looks like this. So now this is another term that's very important in a reaction. Sometimes between steps, you get what's called an intermediate. It's something that you can actually isolate. It's a species that you can trap, isolate, and characterize. So the intermediate is going to look like this. So this is my salicylic acid. This is my oxygen. Now it has H here. Now it has a bond. Don't panic when I draw this. It's okay. I'll explain it. Right. It's going to have a bond to that carbonyl, which also had a CH3 attached to it. And then this is here. This is the oxygen. And this is the other half of the anhydride. Right. And then here, this oxygen has a plus charge. So that's what happens when I attack that carbonyl. That oxygen makes a bond to the carbonyl carbon, and I'm gonna circle it in yellow so we can keep track of it. Right here, same carbon. Right, that's the addition part. So after the addition, you get an intermediate. I'm going to abbreviate addition. Right, you get an intermediate, and then that intermediate is actually now going to decompose, and that's how we're going to get that acyl group out here. So we're going to take these electrons and push them here, and then break that CO bond right there. So here, and now we're going to get another intermediate. This doesn't change. This does. The hydrogen is still here. This is positive. And then that plus this. And that's negative. All right. This oxygen up here is still positive. All right. So what's the intermediate decomposes? Call it decomposition. It's actually elimination. All right. So we did an addition first, and then we're going to follow that up with this elimination step. Right. Now, let's go back and look at the two products up top. These are the products. I have acetylsalicylic acid or aspirin. And then I didn't give you the name of this one, it's acetic acid. All right. Now, let's go back down to here. How could I get those two things from these two things that I have drawn on the right in blue? What can I give to this acetate ion from here, from this structure? What can I give to it to make this, make my two products? Anybody?
A hydrogen?
Hydrogen. And I have one right here. That's excellent. I can give up this proton right here, which is readily accessible because oxygen is positive, right? So if it's positive, it's dying to be neutral. And so in order for it to become neutral, it can donate that proton. And so we're going to do what's called a proton transfer. Right, that hydrogen, we'll call it a proton. So this part right here is an acid-base step, whereas the first part was a nucleophile electrophile step. And what you'll find out a lot of times is that you kind of go between those two modalities, right? You go from nucleophile to electrophile to acid-base, sometimes in the same reaction. Right, so that proton transfer is going to happen. Now, this is a kind of $1 million question. I just want to see what you're thinking, right? In order to pick up that proton, that oxygen is going to have to give up a pair of electrons, right? Which way should I draw my arrow? Anybody? If you watch the video, you saw it already. Or you saw something similar to it. So I'm gonna start at this pair of electrons right here. Which way should I draw the arrow to show that that oxygen is reacting with the proton? All right, this is my base. And so I'm going to draw it from the base to the proton always. And then when I break the bond between the proton and oxygen, I'm going to give those electrons back to oxygen. Don't panic about that either. We got a whole section on acid-base chemistry that we're going to learn. And now you'll have a preview. So this will give me my aspirin, plus acetic acid. Right? And I know in the video it showed you the acid catalysis, so that's sulfuric acid in there. And that just helps to speed the reaction up because it makes the anhydride more reactive. All right, questions about anything? Any questions?
Can you scroll down to the last, yeah, right there. Back.
All right, so again, don't panic about this because we're going to have a whole section on nucleophiles, electrophiles, and acids and bases, and pushing arrows. But I just want to introduce you to it because, again, why not? It's better to be exposed to it now and then see it again and have some familiarity with it as opposed to not seeing it and then jumping in cold. So, but if you watch the video, the mechanism was in there. It's slightly different because I did show the acid activation, but it's okay. All right. So on today with this aspirin synthesis, the way this is carried out, it's one thing to show it on paper. You actually are going to see the experimental setup, but I'll just write this out. So you're gonna have hot plate. And then on that hot plate, you have a water bath in a beaker, 600 or 400. Right. And then in the water bath, you don't have to write this down, by the way. In the water bath, you'll have an Erlenmeyer flask. Right. And then the flask, you're going to have salicylic acid as a solid. And then you're going to add in acetic anhydride. So that's added in. Right, and you heat this until all of the salicylic acid is dissolved. Right, and usually at the point where salicylic acid is all dissolved up, that's when the reaction is complete. So the reaction calls for, and you can write this on the data sheet, it calls for 6.9 grams of salicylic acid. It calls for 7 milliliters of acetic anhydride. And on that data sheet, if somebody would look up the density of acetic anhydride and just Google it, and when you find it, just unmute and say what it is.
(1.08 grams per cubic centimeter).
So 1.08 grams per milliliter. All right, so let's go ahead and convert that into grams. So 7 mils. I want to get rid of milliliters, so I want milliliters in the bottom. So that's just going to be, we know that density is mass over volume. So density times volume will be mass. So it's a simple multiplication. So I'm going to do 7 milliliters times 1.08 grams per milliliter. And that milliliters are going to cancel. Can somebody calculate that real quick? It's 7.56, something like that. Is that right?
Yes.
7.56 grams of acetic anhydride. That's important. On the data sheet, one of the boxes asks you for moles. Is that right?
Yes.
You can't convert it. You can't get to moles without grams, right? Unless you have a concentration, which is in moles per liter, and you have a volume. But if you heat for what we're doing right now, we need to get this into grams. So somebody look up the molecular weight of salicylic acid. And then somebody look up the molecular weight of acetic anhydride. And then while you're looking that up, you can fill that information in on the data sheet. The density of acetic anhydride, the molecular weight, the actual amount, well, the required amount and actual amount, because I think both of those blocks are on that handout.
The molecular weight of acetic anhydride, 2.09 grams.
Can you say it again? It kind of chopped up.
For acetic anhydride, it's
Mhm.
102.09 grams of
Grams per mole. Okay, great. What about salicylic acid?
It's 138.032.
Excellent. So now we can find the number of moles of each one of these, right? We have the molecular weight, we have the masses of each one, so we can find the moles. So let's do moles. Sorry. iPad. Moles of salicylic acid. So you know molecular weight is grams per mole. So we can manipulate that. Anytime we have a relationship, an equality like that, we can manipulate it. So that's going to be molecular weight times, grams over molecular weight will give me moles. That's with anything. If I have the mass and the molar mass or molecular weight, I can find a number of moles, right? So I'm going to take the grams of salicylic acid, which is 6.9 grams, divide that by 138.03, is that right? Yes. Grams per mole. And that's going to give me the number of moles. Somebody help me out. Just go ahead and divide that. Anybody got it yet?
I got 0.0499.
So let's just round it up.
Yeah, that's what I was gonna say.
0.05 moles. And then what about moles of acetic anhydride? What about that? We calculated that to be 7.56 grams divided by 108 point, where is it? 09. I'm sorry, 102.09. Sorry about that. And sorry for all the scrolling. 102.09 grams per mole. So that's going to give me the number of moles of that.
It's 0.07.
0.07 good moles. All right. Now, the question, and I'm going to ask this question to see if you remember this from GChem, and then we're going to get started with the other part of this discussion. Which one of those do you think is going to get used up first?
Salicylic acid.
Salicylic acid. There's less of it present. Is that right? So you have 0.05 moles of that. It's going to react with 0.05 moles of acetic anhydride, and you're going to have 0.02 moles of acetic anhydride left over. So we can already go ahead and identify this as the limiting reactant. That's going to control how much product we get. All right. Everybody okay with that? Any questions about that?
Is the actual amount, required amount, the same, or is that different?
Well, no, the
Like
actual and required, so the required is 6.9. The actual is what we're going to see in the video.
Okay, I
Sometimes
got
it
you.
may be a little bit more, a little bit less, but you want it, the goal is to try to weigh out this number exactly if you can. But of course, we don't live in a perfect world, right? So you're always going to have a little bit of a discrepancy as far as how much you actually weigh out. So the required amount is 6.9 for salicylic acid and 7 milliliters or 7.56 grams for acetic anhydride. Did that answer your question?
Can
Yes,
you
it did.
repeat
Thank
what
you.
you just said?
Yeah. So
For the required?
the required is what we have prescribed, right? So here, the required amount of salicylic acid is 6.9 grams. The required amount of acetic anhydride is 7.56 grams. That's what you put in the table.
Okay, thank you.
But the actual amount will actually, we're gonna see in the video that it might be a little bit less or a little bit more. So, but then you still can, but you can still calculate your amounts and things like that based on what you weigh out. But you want to get as close to these numbers as possible.
And I have a question.
Go ahead.
The densities
Mhm.
for them, did we say that already?
So yeah, salicylic acid is a solid, so it doesn't have a density, but acetic anhydride, someone looked it up, and the density they gave was 1.08 grams per milliliter.
Thank you.
Mhm. So this is good. That means that you're following along and you're filling that data table out. Anytime you do a reaction, you want to have a data table like the one you have in front of you, with your reagents, the density, molecular weight, moles, the amounts, and that way, when you get ready to calculate your percent yield and your theoretical yield, you can do that without having to ask a whole lot of questions. Right? Let me go ahead and tell you right now, since this is limiting the salicylic acid, this is what this number of moles will be used to calculate theoretical yield. Right? Right. So someone go ahead and let me go ahead and explain that part too. And then we're going to jump into this video. It's a short video that we're going to watch and walk through it. Just for the synthesis part. Can somebody look up the molecular weight of aspirin itself? Because there's a box on here that asks for theoretical yield. Am I right?
The molecular weight is 180.158 grams per mole.
All right. So let's talk about this calculation of the theoretical. This is not percent yield, it's the theoretical yield. So the theoretical yield is the amount of product expected or produced by the limited reagent. So it's the amount of product that the number of moles of limited reagent is capable of producing, right? And the theoretical yield is always in grams. Right? And so I'm going to give you a very, very simplified way to calculate this because we've already identified the limited reagent. That's the first step to calculating theoretical yield is to figure out which reagent is limiting. So the way you do this is you find the limiting reactant, and we've already done that, right? And then you look at your product. We're going to multiply the moles of limiting reactants times the molecular weight of the product. It's a quick and dirty way to think about it. Once you identify the limiting reagent, then it's just a matter of taking that number of moles and figuring out how many grams of product you're going to get from that. Right. So up here, we said that this was limiting. We said that this was 0.05 moles. This was 0.07 moles. So 0.05 is limiting. And we're going to use that. So we're going to say the theoretical yield is going to be 0.05 moles. And I can actually, let's go ahead and let me show you, let me go to the old way. Well, not the old way, the CHEM way, right? And we're going to take moles of salicylic acid and turn it into moles of aspirin times 1 mole aspirin over 1 mole salicylic acid. So that's going to cancel that out. The 1-to-1 part, that's the ratio, the stoichiometric ratio. You get that from the equation. And if you go up to the equation and you look at the equation itself, it's already balanced, right? So we went from, this is 1, that's 1, and then that's 1, and that's 1. So everything is balanced. So we could say, without having to go through, because I know in GChem sometimes that's not readily apparent. You have to balance it. Sometimes everything is not 1-to-1. But if everything is 1-to-1, we can say that 1 mole of this is equivalent to 1 mole of that. And so we can use that as our ratio. Right. So that's how we're able to figure out how to interconvert between moles of salicylic acid to moles of product. All right. Questions about that before we move on? All right. So let's go back to here. We know the answer to this equation right here is 0.05, right? We just multiply that times 1. So we can say that is 0.0 moles of aspirin. And we know now we know that, and we also know the molecular weight of aspirin, which is 180.16. So we're going to take that times 180.16 grams per mole, which is the molecular weight of aspirin. All right, somebody tell me what you get from that. So 10% is going to be 18. 5% will be 9.
9.01.
9.01 grams. This is my theoretical yield of aspirin. 9.0. That's how much we expect to get if we take 0.05 moles or 6.9 grams of salicylic acid, react it with 7 milliliters of acetic anhydride, run the reaction, purify it, well, filter it, purify it. That's what we expect to get. All right. So you can go ahead and fill in that box that says theoretical yield. That the theoretical yield is 9.01 grams.
What did you say the molecular weight for the aspirin was?
180.16 is right here. All right. Other questions? Anything?
I have a question, but it's unrelated. Well, it's related to the lab, but not what you're teaching right now. Are you going to upload the
This?
recording?
Absolutely.
Okay.
Yeah.
When
It'll be
should we
on,
expect that?
I'll do it this evening, and I'll send you a
Okay.
link to it.
Perfect. Thank you.
Yeah, always. Anytime we meet and discuss anything, unless I forget to hit record, I'll upload it.
So just to be clear, the theoretical yield, it came from the limiting reagents, which
Mhm.
was 0.05 multiplied by the molecular weight, which is the 180.
Yes.
Okay.
All right. Other questions? All right. Let me switch gears. We're going to actually walk through this. I mean, I just got to reshare my screen. 1 second. And move this out of the way. This thing pulled up. That's all right. So let me find the playlist, and we're going to just. Oh, shucks. It's not where I want it. Everything is so slow. Let's see. Let's go to this playlist. Okay. Let me go to. Wrong playlist. God dang it, Russell. 1 second. Let's see. All right. All that's gonna be here, so you'll have a find that. All right. So let me. And we're gonna weigh out. Get this out of the way. 6.9 grams. And all the introductory stuff that we just talked about, I'm just gonna skip it because all that's in here. All right, so normally, while I'm waiting on this to load up, normally when we come into the lab, you'll have your materials up front, and then you'll also have a balance. And we normally weigh out the solid on a piece of wax paper or a weigh boat or an aluminum weigh pan or something like that. So I'm just gonna let this play for a minute and then I'll interrupt in a second. So grab so this is the way we're gonna set this up. Let me show you that. And can everybody hear that?
Yes.
Yes.
Everybody has a 400 ml beaker. So I want you to take that beaker and put about 100 milliliters of tap water into it. All right, so we have let me turn the camera back around this part. All right. So we got a 400 ml beaker, and we're gonna put tap water. We're gonna use this to make what we call a water bath. All right, so that's how we're gonna heat this up. In organic, you do not use open flames. I know you used it in CHEM, but that's because you didn't work with stuff that was bottled. In organic, everything is bottled. Everything is given off vapors. And if you light a Bunsen burner in here with this acetic anhydride, just poof, be gone. Everybody, all of us gonna be somewhere, East Alabama or wherever. It's gonna take about 3 hours, so I don't know how many of us gonna survive. But you always want to use a hot plate, and you never use an open flame, right? In organic. So we're gonna put some tap water into here, so we can start our water bath. So go ahead. So we got a water bath that we're gonna set up. Turn the camera back around. So you can see on the hot plate, excuse me, we have a water bath here. We're gonna turn the hot plate on and start that water to boil. So go ahead and turn your hot plates on and put the water bath on there, because while the water is heating up, you can be weighing out your stuff. One thing about lab, you want to be as efficient as possible. Everybody always asks, you really gotta stay at 4 o'clock? Well, stay as long as you have to stay, but you can make the time a lot shorter if you actually work efficiently. All right? So I'm gonna grab my goblet. I would put it probably on about between what you got. This is the point you work with. Put it on that zoom in, everybody that's here. Look on the handout. See that block that says molecular weight for salicylic acid? Put this number in there. So I'm going to skip through because we've already discussed all of that. We talked about where to fill out the data sheet, where to put in the molecular weight, all of that. So I'm going to skip through that to the weighing part. All right, so you can see the balance is set up with a sheet of wax paper, and then the salicylic acid is here, and then we'll take a scrupula and just add it. And then we're going to weigh out 6.9 grams. All right, we had 3.62. So I can kind of gauge and see how much I need. And just for the record, I'm the GOAT when it comes to weighing out stuff. I really am. Weighing and pouring. You can disregard that comment. No, that's not up for discussion.
Might have to challenge you to that.
Come on with it then. What you waiting on? Come on, Cleveland. Ignore my goofiness. All right. Up and down.
incorporate. But what the sulfuric acid does,
So we've already talked about the amount. So I'm gonna skip forward to the addition part.
the next step is gonna be to add, you got two more steps. We're gonna add acetic anhydride.
And you can see right here on the screen that beaker, the Erlenmeyer flask that's on the desktop, on the bench top, all that's in there right now is salicylic acid. So it's just a solid, it's the 6.9 grams that was weighed out, transferred directly to the flask. And then the other reagents are going to be added by syringe. So the acetic anhydride is a liquid. So you add that by syringe. And then the sulfuric acid is also a liquid. We're going to add that with a dropper. So you'll see that.
Directly to that Erlenmeyer flask. And then after we do that, we're gonna add some sulfuric acid as a catalyst. It says 6 to 8 drops. And what that sulfuric acid does, well, y'all can't see this, but what the sulfuric acid does, you can see that on the board, the H2SO4, that's gonna actually protonate this oxygen right here. It's gonna do a proton transfer with this oxygen and activate it so that this hydroxyl as a nucleophile can attack that carbon needle. So that's the purpose of the sulfuric acid. So we're going to add first. We're going to add the acetic anhydride in 7 milliliters. So those of you who are watching, I'm going to focus on this right here. You can see the flask on the table. And I got a little syringe I'm going to use, and I'm going to just come around for each other. Man, now your hot plate is not lazy. It's aggressive. Yeah, I feel you. I feel you. Go status. You heard it. 3. We're going to add this directly. In the handout, it says to add the acid on an ice bath, but we're working on a smaller scale, so we're not going to have to cool it down. All right, so don't worry about that part in the procedure. Everything is good. Take my word for it. All right, and this reaction is done under what we call neat conditions. That means no solvent, right? It's neat. Okay. So that's 7 mils of acetic anhydride. Hopefully y'all can see me. And then I'm going to add in 6 drops of sulfuric acid.
So normally when you add that sulfuric acid, like on the procedure that's actually on Blackboard, it'll say to put the flask on an ice bath. But since we cut the reagents in half, and the exothermicity is not as pronounced, right? It won't generate as much heat. We just added it at room temperature.
All right. So that's six drops of sulfuric acid.
Dr. Russell, where is the handout for this? What is that?
Blackboard, course documents, weekly experiments is the first handout in there.
Okay.
All right. So now, once we've added the acetic anhydride and the sulfuric acid, we're going to take this flask, because you want it to stay hot. If it cools off too much, the reaction won't go. So we're going to take this and we're going to add it right to the water bath. Sit it down in there. And what we're going to do is we're going to heat it until it goes clear. So let me show you. Let me zoom in. Right, you can see right now it's not clear. Right, it's cloudy. But the longer you heat it, the more the reaction is going to go. So we're going to leave it in the water bath, and all you got to do is swirl it. Every now and then, I want you to swirl it to keep it mixed. All right? And I'm going to keep the camera right there. And I'm coming around to the other groups.
All right. So when you're doing this reaction, you want to again, have a hot water bath. You don't want to just heat it directly on the hot plate because that'll just evaporate off the acetic anhydride. It's got a really low boiling point. So you want to heat it on a water bath. You swirl it until it's clear. And I'm trying to find the spot on here where we can see the clarity. Let's see here. I think.
Once it goes clear, you just let it keep heating for another 5 minutes and it's good. All right. What about you back here? You good? Is it going in? Yeah.
Let me back up.
What you can do is, boom, you can just stick the water, just let it keep heating for another 5 minutes and it's good. All right. What about you back here? You good? Is it going in? Yeah. Hold that up. So you can see his is gone clear.
So this is what you want to see. Like when you run this reaction, you want to continue heating it until everything is clear, right? You don't want any particulates, any solids floating around, nothing. You want everything to be clear. And then once you do that, you heat it for an additional 5 minutes, and then you take it off and let it cool to room
That
temperature.
means the reaction is almost complete. And same here, you want to turn that, get that last little piece reacted. So let me show y'all that part too. Like if it calls for cold water, what you can do is, boom, you can just stick the water, take the base off the graduated cylinder and just stick it down into ice, into a cooler or an ice bath or whatever you want to do. Omari added water to his and then immediately turned cloudy. And so what the water does, aspirin is not soluble in water. And so what we're going to do is force the aspirin out of the solution by adding water and then cooling it down on an ice bath. That's the colder the solution gets, the more insoluble the aspirin becomes. So we added 40 mils of water. And so now what we're going to do is we're going to put that on an ice bath and watch it crystallize. So for the setup for your filtration.
So let me back up. So once you finish the reaction, you have to add 40 mils of cold distilled water, right? And you just heard the explanation. Water, aspirin is insoluble, so the cold water is going to force it out of solution. This is not a recrystallization. It's more like a precipitation. So you want it to fall out quickly. And then after that, you sit your aspirin sample on an ice bath and let it sit. Normally we'll wait about 20 or 30 minutes to get as many crystals as possible. And then the final step is a filtration. And we do what's called a vacuum filtration. So that's what this part of the video is going to outline right here. It's a vacuum filtration.
You need a beautiful funnel. It's this little ceramic funnel right here. I'm gonna send y'all a video. I got a video with the glassware on it, so you can at least have that. But you need a Buchner funnel. You need a filter flask, which is this, and you can see the little nipple on the side. That's the part that connects to the aspirator of the sink, and that's how you get your pressure, right? Because the sink is gonna pull vacuum once you seal it up, but you can't seal it up without either a stopper or a filter adapter, which is what this thing is right here. So this goes here into your funnel, and then you just sit it down in here, right? And if it's too big, if the filter flask is too big, you can flip it over like that and sit it on top. And both ways you're going to get back either way. It doesn't matter. All right, I think these filter flasks, the mouth on them is too narrow for these, but we're going to make it work. Always make it work. All right, so I'm going to turn this around. Right here, you can see on the sink, you see the aspirator, the little nipple coming off the side. So we're going to set this up. And that's tight. Because it don't want to do right. So we're going to take a piece of a coffee filter. This is a regular coffee filter, 100, 200 for $1 at Walmart. Get that down into here. I know it's kind of big, but that makes it better at the end, right? Because then you can just lift it out. And the way if you want to seed it, if it doesn't want to act right, you can always just drop a little bit of water onto the filter to seed it down into the funnel. So let's get those set up for everybody, and we're gonna roll. So we need filter and filter. Right. Anybody got any questions so far? Y'all good? All right. So I think we got everybody. Y'all want to go? What is one X? 2 4 X. No one should worry. All right. I think we're ready. Thanks. So let's continue to take the aspirin out of the ice bath and swirl it around a little bit to get it off the sides and all that stuff. And let me see it before you filter. So this is what you want right here. You want your aspirin to be a white crystalline solid, right? And so since we have that, we're gonna
So that aspirin that you saw was actually what we call crude, like impure aspirin. And that's really like the first step of the reaction. That's all it is. It's just making that crude aspirin. And then the last step is to filter it. Because you want to keep the solid and filter off the other impurities.
Sometimes if the aspirin is real chunky, you can break it up. Right? That's a physical change. That's not a chemical change. So it doesn't matter if you break it or crush it. It doesn't matter, right? So we're gonna take this, I move it around some. Right, so I got a glass rod, and I'm just gonna chop that up a little bit. So when I get ready to filter it, it'll all come out. There you go. So when you filter it, you're gonna turn on the water supply. And while that water is going, it's gonna pour that on. And I think don't you have to rinse it twice? 15 or 10 mils. 15 mils twice, 20 mils twice. All right. So go ahead and pour it. Like all of it? Just don't dump on it, but just pour it on. And you're gonna see in the flash, you're gonna see the water start to come through the bottom. Right? So just keep pulling back again. Get all the solid on there that you can, and anything you can't get, just turn it over and tap it.
So normally when you're doing the filtration part, there's always a rinse step where you take that flask, because there's always going to be some stuff stuck to the side, some residue. Just take the flask, you rinse it with cold water, and then you just filter it again. You want to get as much of that solid on that filter paper as possible, because when you're talking about your actual yield, anything you leave behind is going to subtract away from the actual yield. So you don't want to do that. So you want to be able to wash it, filter it, and then when you filter it, we just take the filter paper out and put it on a watch glass and let it dry to the following week. Let me see if that step is on here, because there's no sense in just all right, here we go.
Any other we can look it up, but since it's catalytic and it's just such a small amount.
Yeah, so this is the final, like the last thing you'll have to do is take the filtrate on the filter paper and you put it on a watch glass and you just let it dry till the following week. Normally, you could take your filter paper and weigh it. We didn't in this case, but under most circumstances, you want to weigh the filter paper before you use it. And then that way, when you come back, when it's dry, you can just put it back on the balance and take the difference to get the amount of product that's on there. We didn't do that here because the coffee filters are pretty easy to handle. Once they dry, you can pretty much scrape off like everything that's on there onto another piece of wax paper or something like that without losing anything. But under normal circumstances, you always want to weigh your filter paper before you use it to filter your product. Any questions about, because that's the end of this walkthrough, by the way. And this just made me nostalgic for going and being back in lab. It sucks that we're not there, but it's coming though. So any questions about anything?
I have a question. For the acetic anhydride,
Yes.
is the required amount was it 70 milliliters?
No, 7 milliliters.
7 milliliters.
Yeah.
Okay.
If you put 70, that reaction will never happen because it will be too saturated with acetic anhydride, so it wouldn't happen. But it's 7 mils.
Okay. Thank you.
Any other questions?